Welcome, everyone. My name is Michelle Branzaleski. I'm the Global Marketing Manager here at Control Station. We're going to start in a minute. We have a large group for this webinar this morning, and people are signing in, so still signing in. So we're just going to wait another minute. Please bear with us. Thank you. Okay, I guess we can get started. Again, thank you for the privilege of your time today. My name is Michelle Branzaleski. Our webinar today is how are oscillations affecting your process at your plant? So with that, I'd like to start the presentation. Next slide, please. With me today, I have my colleagues, Bob Rice, he's the VP of Engineering, as well as Brett Beauregard, he's the Director of Product Development. Next slide, please. So for those of you who are not familiar with Control Station, I just want to kind of tell you a little bit about us. What we aim to do is partner with our customers to solve their process control needs with a combination of world-class software and expert services. We have offices in the United States as well as Ireland and have successfully deployed our solution in support of facilities located in over 70 countries, and this is still growing. We are proud to partner with 1 out of 2 manufacturers listed on the Fortune 500. So with that, can I have the next slide, please? All right, we're going to get everyone involved this morning. I am going to launch a question, and you should see it in like a minute or so. Give your screen a second, and all you have to do is take your mouse and click on all that apply. What do you think at your facility, your personal facility, is costing you money? Product quality, lattes in the break room, production delays, equipment damage, safety hazards. So with that, I am going to let you answer. And we'll leave this up for about another 30 seconds to give everyone a chance to participate. Just so everyone knows, this is our last webinar for 2023. So I am working on the 2024 schedule. And if anybody has any topics that they would like us to address, feel free to send me an email. Everyone has my email address from the invite. All right. Looks like we got a good polling here. I'm going to close this and I'm going to share the results. Oh, there we go, share. So, looks like the majority of people feel that in their facilities, equipment damage is costing them the most. Then it looks like product quality, safety hazards, and production delays. So thank you for participating in that. We will have more coming up. With that, I would like to hand it over to Mr. Bob Rice. Bob.
Excellent. Thank you very much. So what I'd like to go through in this webinar is kind of how oscillations are impacting your process, and to kind of lay the groundwork for why we even care about oscillations. We need to understand how they actually impact our ability to optimize or run our operations at their most efficient, right? And we've all walked into plants or walked into our own facilities and taken a look at loops or pieces of equipment, and we can visually inspect them and get an idea that, hey, they're cycling, they're oscillating, they're swinging around, and they've got problems. And you walk over to the operator and you say, hey, look, you've got an oscillation over here. And their response, half the time is, yeah, it's always done that. Don't worry about it. It's fine, right? And a lot of times you're kind of stuck, right? How do you take that fact that the loop is oscillating and actually go and get them to fix it, right? Get either the maintenance staff to go and investigate the valve or the equipment or the instrumentation or the tuning or whatever it is that's causing that oscillation. How do you drive that that conversation forward. And one of the things that we've done to try to help people understand that is to explain it's the oscillation itself may cost you some money, but what it's really doing is it's preventing your equipment, preventing your process, your unit operations from running at their most efficient, right? And in the example I give on the screen here, we start with kind of the status quo poor control, and then we can go and say, look, we've identified it, and then we go and we correct it, right? And we take that high variability and we decrease the variability, we remove the cycling, the oscillations, we do it through any manner of different things, right? Well, once we've done that tuning and that optimization, we kind of have to take a step back and ask ourselves, okay, now what? Right now we've gone and tuned it, we've made it better, but have we really, moved the bars forward on, generating more revenue out of whatever piece of equipment this is? And the answer is, not necessarily a huge amount of revenue is saved just by tuning or fixing the valves. But what it allows you to do is take that next step forward and do that optimization, right? Where you can move that set point or move your constraints, move your throughput to operate a little bit closer to whatever production or operational constraints that you have. So poor control costs you money. Oscillations cost you money because they inhibit the ability for you to actually run at higher rates or run at closer to constraints, whatever it is. And in this example here, we took variability and we decreased it and we moved the set point 1 or 2 degrees closer to constraint. And because of that, we were able to probably use 2 or 3% less cooling in this particular case. And if you went and tuned all your utilities loops that use cooling or steam or whatever, and were able to, eke out a 1 or 2% improvement, that can really start to add up. And we've done projects with customers in the past who have just focused on utilities loops and gone through and did the optimization, the tuning, the analysis to identify where the variability was highest, go and tune it. Maybe they decrease the variability by 50% or 30%, and then they would just move the set points up and down based off of how much variability they removed out of the system, and they were able to, gain a 1 or 2% less utilities cost at their site. And that number was actually staggeringly large in a lot of examples, right? It would be, a few $1,000s a loop to hire, per year of savings with, really what is minimal effort. And it's those types of opportunities that are available at your plants where oscillation is costing you money. So what are the sources of oscillation, and how do you detect those from your sites? So when you're thinking about control loops and valves and flow loops really get the kind of the brunt of everything, is what really causes your control loops, your valves and so forth to oscillate, right? And there are a lot of factors that can cause valve oscillations and so forth. And we're going to go through kind of after the next poll question, kind of in details to these different areas and what does it mean and how do you detect it and how can you interpret it and what kind of improvements can you make there. But we're going to talk about oscillations that are primarily due to, valve nonlinearities or the wrong type of valve. If you have valve stiction or dead band associated with it, you have incorrectly sized equipment, right? Do you have valves that are way too large or way too slow? And, how do the PID controller settings impact the performance of a loop, the stability of a loop, right? So all these things can cause oscillations within the system, and we're going to talk about each one of those, but you have to be able to identify and detect these types of systems, which take us into our next poll question.
Thanks, Bob. Okay. As before, give it a minute to come up on your screen. Take your mouse and select all that apply. So you personally, how do you detect oscillating valves at your plant? Visual inspection, performance monitoring, you leave it up to, the knowledge of your fortune cookie from lunch, control system analysis, or data analysis and trending. So if you can take your mouse, please click that all that apply to you. And I will give this another 30 seconds and we will share this. I also like to make another plug. In 2024, in addition to our webinars, we will also be doing podcasts, and I will be sending out information on that. Please remember to subscribe to the podcast so when one is uploaded, you are immediately notified. All right, it looks like we got a good sampling here. I'm going to share it. One moment. Okay. So 81% data analysis and trending, visual inspections, then performance monitoring. No one selected my fortune cookie. Come on, I thought that was brilliant. Control system analysis. All right. Thanks again for participating. And I will hand this back over to Bob.
Excellent. So, even based off that poll question, I knew what the answer was going to be before we had the poll question because it's the most common one. It's looking at data analysis and trending. You're identifying oscillations and detection by looking at the process data, right? Looking at the trends of the system to be able to say, hey, is there oscillation in the process variable or in the set points or in the production or the rates or whatever it is, whatever variables you're looking at on your HMIs and your operator stations, you're seeing cycles in the data, right? And that tends to kind of throw you towards the direction of where the oscillations are impacting your system. But when you're taking a look at your process as a whole, you've got kind of the visual inspection of equipment, right? I've gone and done enough plant tours in my time where you're walking through, you're doing inspection of equipment, you're looking through, and you can almost visually spot which valves are maybe not exhibiting the behavior that they should because you're seeing, perhaps you see the positioner kind of bounce around or wobble around, or you see steam leakage and especially on steam loops kind of pushing out through the stem and so forth, and you can kind of hear the valve kind of move around a bit, and that visual inspection can really unveil a lot of poor behavior. And whenever you think there's a control valve of issue, it's always good to go and do some sort of visual inspection. Looking at performance monitoring of your system, looking for particular patterns that you have in the data that we'll talk about here shortly is a good way. Control system analysis, looking at your controller behavior, your closed loop response is really good. In that control system analysis, I'll also add, a lot of systems have valve feedback and have valve analytics and so forth in the DCS. You're pulling out some of that smart instrumentation on those smart valves, and the valves are starting to send notification and alarms and events up saying, hey, something's wrong with me, go fix me, right? You're not having to wait for that type of stuff, and that's great. That's a great direction that this industry is moving in. And then traditional data analysis, trending, just staring at the trends till you see the cycles and so forth present. So there's a lot of steps that you can go to go and analyze this. So let's talk through some of the behaviors of your control loops, especially associated with valves, since they tend to be the root cause of a lot of cycles and oscillations within your system. Let's talk about some of the different behaviors that can crop up here. And so valve stiction is one of those things where the valve is being requested to move, and it's not actually doing anything, right? It's physically stuck, right? And so you can see the trend there. The blue line is starting to move up, right? And that blue line causes a problem in that it's not actually moving the valve, right? The output's telling it to go, 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 go. Then all of a sudden it actually starts to move the process, right? It pops the valve, flow goes too far, and now we cycle back the other way, and we get these cycles, right? And with valve stiction, this is really common. If you tell a valve to move 0.25%, it may not move, but you're expecting to run these things under closed loop. So I'm going to bring in my colleague here and kind of ask him a few questions. When you're dealing with valve stiction, how do you deal with that from a tuning standpoint? How do you fix a valve with PID settings?
First of all, good morning, everybody. So you can't really fix stiction, unfortunately. So the valve is what it is. The nature of reality is what it is. It would be nice if you could wave a magic wand and take care of it. So you have this kind of dead area where the valve is you need to ask and ask and ask and ask and ask before you get enough kind of steam for it or a head of pressure to jump the valve. But if you want to kind of minimize the oscillation effect, here you are kind of chopping back and forth, you can change the tunings, specifically the integral term. So what we're seeing here is those kind of linear sawtooths on the controller output are the integral term kind of asking for more winding up. So basically you're above set point or below set point and that error is building up, and the line is the integral term kind of asking for more, asking for more because it's not happy. And then all of a sudden getting very unhappy because now it's on the wrong side. So what you can do with tuning is you can kind of change the rate at which that accumulation occurs, right? So if you make the integral term less aggressive by tripling it, quadrupling it, you can change the rate at which those lines are increasing or decreasing, and that can affect the period of oscillation. So it's not going to eliminate the oscillation, unfortunately, because reality is what it is, but it will ask more slowly, ask more slowly, ask more slowly before it blips. I will say that this is really only useful if you've got a steady process, because if you have to do numerous load changes and things like that, you're going to need that integral term to help. But that's something you can do if you have identified that there's an issue and you've got it on the you've got it on the maintenance list for the next shutdown or whatever, and you just have to limp along. That's something you can do. You can make the integral term more conservative, and that can kind of help you with this this behavior.
Thanks, Brett. In regards to other valve performance issues, there are things like deadband and hysteresis and backlash. Can you give a 30-second or a 45-second difference between deadband and stiction and backlash?
Sure. So with deadband and hysteresis, everything's fine as long as you're going in the same direction. Basically, what winds up happening with these guys is that when you're going in different directions, so stiction is a problem because you have kind of you have some kind of resistance that you have to overcome. With deadband, it's more that there is slop in the actuator, so there might be a gap in the valve between the valve stem and the actual kind of closure member, and as soon as you're engaged and moving in one direction, everything's fine. But then when you have to change direction, the actuator has to move through a dead space before it can actuate in the other direction. And you kind of get a similar effect with stiction, where it's kind of like once you're at set point, it's like you have a tendency to go too far, and then when you're moving back and forth on either side of stiction, the set point, it can cause issues similar to the oscillation, where the PID wants the process to respond exactly, but because of that dead space, it tends to overreach. And then hysteresis is not as big of an issue, but this is more where when you change direction or when you're moving up versus moving down, the valve stem might not be in the same position, or the actual closure member might not be in the same place. I would say of the three, that one's the least important in terms of oscillation. But again, if you have a situation where the PID isn't getting exactly what it wants, it tends to overreach, tends to overshoot, and then has to roll back to, it has to back off what it did, and then you can kind of get these oscillations.
Excellent. Thanks, Brett. So now that we have all of these issues that we know exist in our valves, and let's be honest, every valve has at least some small amount of stiction. It may not be in the operating range or the movement at which your valves typically stroke, but it exists, right? So how do you detect valve stiction? What are the ways to go through and do testing? So Brett, what are the kind of the manual and the automated approaches for detecting this type of poor behavior?
I mean, with stiction, it's right there on screen. But yeah, so basically what you'll do in a case when you want to test for these things, first of all, you can usually visually identify if you kind of envision this ask, jump with stiction. If you want to quantify how much, you want to get really detailed, you can kind of do what you see on the screen here. So you can you've presumed that you have to overcome a certain amount of stiction before the process will respond. So you can, start slowly incrementing up your valve, and you see nothing, and you see nothing, and you see nothing, and you see nothing. And then finally, I think in this case, after moving 1.1% in the valve, you see a jump. Okay, so you've now quantified your stiction. I don't think we have a slide for deadband, but basically what you would do with deadband is that you would engage, move in one direction a certain amount so that you know that you're engaged in that direction. Then do a step up in the same direction and then a step down. If you have no deadband, you should return exactly to where you started. If you have some deadband, you won't return to the same value, and you can assume that the difference is caused by some slop. So these are things where in manual you can move your output in a kind of predictable way, and you can quantify deadband. Another valve issues. Another deadband test would be that you kind of move up and down in larger and larger steps until you start observing responses, right? So you can assume that you can kind of wiggle the actuator back and forth until you can see that you're actually engaging, with larger and larger steps. So those would be kind of some valve tests that you could perform manually to identify what's going on with your stiction or deadband situation.
Well, what about a way to automate it? Are there tools or methodologies for calculating it without doing all these manual tests?
Sure. So, I mean, obviously we have a tool that will do that, and it's a relatively complicated, I think it was like 70,000 lines of code at last count. But there are other kind of more simple methods, kind of more textbook stuff. If you have a standard looking kind of set of stiction, you can if you can go back a slide, Bob, go back a slide. So stiction tends to have a very kind of noticeable shape, right? You have this kind of almost a square step up and down with maybe a first order kind of response, and then on the bottom you have this kind of sawtooth. And so you'll see a lot of kind of published statistical methods will try to leverage this, right? They'll try to kind of identify this type of behavior and compare, maybe the shape of you can kind of see almost like a curved, so this is a little bit zoomed out, so you'll see sometimes more like a curved sawtooth on the process variable, and then down at the bottom you'll see a kind of fixed set of triangles. And so there's some ways that you can identify, the area of the rise versus the fall and things like that. What we do with our metric, without divulging too much, since there's some secret sauce in there, is we will kind of we'll kind of presume that the valve does have stiction, right? We'll say, oh, does it have 1%, or does it have 0.5%, 1%, 2%, et cetera, stiction? And then we'll see, we'll look at the output and we'll say, okay, well, if the valve had 1% stiction, what would the valve actually be doing, right? It wouldn't be moving exactly perfectly. It would be jumping behind this value. And so then what we'll do is we'll say, okay, we've guessed that you have 1% stiction. That would mean that the valve is doing this, not what the PID thinks it's doing. Which one of those two things is more likely to be explaining what we see in the process variable, right? So if we looked at what we have on the screen here, we would be presuming, if we had 1% stiction, that the valve hadn't moved at all. So instead of seeing this kind of ramped diagonal on the output, we would be seeing nothing, 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 and then it would jump up to 41 near at the end. And we would say, well, that one looks like a much more likely that one seems to be more likely related to what we're actually seeing in the PV. We're going to presume that you have 1% stiction, or in this case, it's showing 1.5% stiction, but we're not positive. And so, there's a possibility. So depending on various kind of statistical methods, we'll say, what, we're about, in this case, about 50% sure. Like, well, yeah, what, it's pretty likely. But in other cases, we might be very, very, very sure that we have stiction. So that's kind of the elevator pitch, if you have a very long elevator, for how we would go about calculating stiction or determining it.
Thanks, Brett. So now that we know that there's different types of poor behavior that can impact the performance, now we actually have to look at the characteristics of the equipment itself, right? And the type of valve, it matters, right? The type of control valve that was put into the system significantly impacts the controllability of that controller. And sometimes that was not necessarily part of the original design. It could have been well, the butterfly valve is the cheapest, so we shoved it in there, or that's what we happen to have in the stock area at the time, and we went ahead and swapped it out, or worse, it had a a nice globe valve in, and then we swapped it for a butterfly valve because that's all we had during turnaround and that was available to us. And the dynamics of those valves can significantly impact the performance of the system. They change their linearity, which is how that control valve moves the flow. So if you move the control valve 20%, 20%, 20%, how much does it move the flow each time? And so you can kind of get an idea of the linearity, just kind of representative of different types of systems, whether it's linear, globe, or ball, or butterfly. And just because you look there and you see, hey, the linear globe is perfectly linear, we should put that everywhere. Well, that depends on the installed characteristics, right? If you've got a pressure drop when you start opening the control valve, the linear globe becomes nonlinear, and something like an equal percentage globe would actually account for that pressure drop. And so it's not just a trivial selection process of the type of control valve. There needs to be thought put into how the process is needs to be controlled, and what is the range, and what is the typical control valve position and flows expected. And if you have oversized or undersized equipment, then you're operating, at that 0 to 5% or 90 to 100% range, and that's just a terrible place for a control valve to operate. It's very nonlinear, and you're going to get a lot of really poor behavior, right? And so if we've got nonlinear control valves, Brett, how do we deal with that from a tuning perspective? What are some of the different techniques that we can employ?
I mean, first, see if you can swap the valve out. But yeah, one of the things you can do is you can. Well, there's a couple things. If it's not a super important valve, so we can see down below, we've got a trend where the blue line is kind of the controller output, and up above you've got the set point and process variable. And you can see that just depending on where we're operating, the same PID tuning parameters are leading to kind of more aggressive tunings in certain areas, and more aggressive performance in certain areas, more oscillatory stuff. And so if oscillation is the name of the game, oscillation reduction, you can just make everything conservative, right? And so then the top of the range would be super conservative, and down below you would be able to dampen those oscillations. If that's not possible, which can happen sometimes, you may need to start thinking about an adaptive strategy, right? So you can adapt your tuning parameters so that between 60 and what are we looking at? It's between 60 and 140, use a more conservative set, but then when you're in the outside, you can use different values. I will add another solution would be also to linearize the output signal. So one of the things you can do is you can kind of straighten the output from the PID, or you can send a curve similar to what we're seeing. So if the difference between your valve and linear is across the range from 0 to 100% is a certain thing, you can linearize your control signal. So you can actually have the output be like, yeah, the PID wants it to be 20%, but I know because of the nature of my valve that it should actually be 50% right now, right? And you can linearize the PID output. So that's another way that you can kind of help the PID get the linear behavior that it's looking for, right? Because the PID is a linear algorithm. It wants the same thing everywhere. So if you can make everything look the same everywhere, that's going to give you your best shot at good non-oscillatory control.
Excellent. And so now that we know we have these types of systems, we have to be able to go and deal with the installed characteristics, right? As kind of Brett had mentioned, the different valves may have different kind of characteristics, and when you install them, it can be a little bit different. So how do you test it, right? So Brett, what are some of the approaches or data analysis that somebody can do without knowing the actual, valve type that's out on the floor, just by looking at process data? What could they do to kind of infer that nonlinearity or detect it?
I mean, it's uncanny, Bob. You have the slide right here that shows.
I know.
So if you look at something like this, like a scatter plot, an XY plot, that's a really kind of good way of kind of seeing, over time, if the valve was perfect, you would expect to see a straight diagonal line where with no kind of padding, where for the same valve position, you got the same flow rate every single time, and it was linearly increasing. That would be the best case. What we have here is we have a situation similar to what, so it's a situation where you need to ask for a lot of valve motion at the extremities to get any change in the PV, but then in the middle there's a steep line. So you have here some nonlinearities with steepness in the middle. And then in addition, you can see here that the width or the thickness of that, the vertical kind of thickness of those blobs there, are showing us that there is some stiction there, because, you know, just because we're at 40%, sometimes it might be stiction, it might be deadband, but basically depending on the path we took to show up at 40, we might be getting a different PV every time, or different input to the PID, which leads to the possibility of valve load changes can also cause this thing, but those will tend to average out. When you have a consistency like this, you're looking more of like a stiction thing, like just, or deadband thing, like everywhere it's the same spacing. You probably want to go out and check for slop in that valve.
Excellent. Yeah, so looking at the dynamic response of your valve at different positions, looking at that XY plot, that is a great way. In fact, that XY plot can also reveal, as you mentioned, kind of the nature of stiction or deadband and other things. The perfect world, it's a nice, beautiful XY, X equals Y line down the middle, but we're never in that world, unfortunately. So now that we have all these control valves, we've kind of understand where the nonlinearities and the poor behavior comes from. How do we actually detect stictions or detect oscillations and cycling within the system? And there's a whole lot of material to kind of jam into 2 slides here, so we'll do our best. But oscillation detection really has its roots around that kind of spectral Fourier transform analysis, where we can take a signal and we can break it into its frequencies and start to try to understand what's going on within a particular signal. Brett, can you do a elevator pitch for what power spectrum is?
How long is our elevator?
Let's just say it's Nakatomi Plaza, right?
Okay,
so
I'm joking.
Couple minutes.
So no, easy peasy. So basically, the way that I like to explain frequency analysis is that if you in your mind's eye can imagine adding together a fast and a slow sine wave, right? So you have one that's maybe oscillating once a minute, and you have one that's oscillating 4 times a minute. If you add those together, you're kind of going to oscillate up in a little bit, and then down in a little bit, and up in a little bit, and down. And so what you can do basically is you can do that backwards, right? So what you can do is you can take any signal and you can break it down into its component frequencies. You can say, you know what, this signal, if it was made up entirely of sine waves, it would be, a lot of this kind, a little bit of this kind, not too many. The amplitude would be pretty small at this frequency, but you can build up a frequency kind of fingerprint for what what the data signal is. So if you have a perfect sine wave, as you do at the bottom here with the disturbance, it would just be a single peak at 17 minutes. This is made up of 100% 17-minute sine waves. But then these other signals, that process variable at the top, there's a lot going on in there. So it might not have anything in there, right? Or it might perfect noise, you would just have like a bunch of chatter. But what we can see on the right is that when we broke it out into its component frequencies, you have a lot of energy near zero there. There's a lot of, kind of extra noise stuff, but then kind of hidden underneath that noise, we do, sure enough, have a peak at 17 minutes, right? So this can tell us that there's an underlying oscillation in there, and that can be very good for relating 2 loops together. It can also be good for an exclusionary thing, right? If one of them has a period of 17 minutes and the other one's oscillating at 12 minutes, it's not very likely that one would be causing the other to oscillate and one would be or whatever. So that's how you would do, that's how it happens. That's what Fourier transform spectral analysis is. That's kind of how it's useful for. And if you have like 4 loops at your plant, it's not really a big deal. But if you have 100 loops at your plant, being able to just quickly go through them and go, okay, these 4 have a pretty dominant oscillation, even if it's not visible. Let's take a look at those and see what the oscillation is. So that's where using spectral analysis can be really helpful.
And I'll add to that. How does it deal with phase shift? So power spectral analysis doesn't necessarily care if the frequencies are right on top of each other. It's purely looking at the period of oscillation, right?
That's correct. So for the plot you're seeing here, if you do a Fourier transform exactly, you will extract the phase and the phase shift and the amplitude. But for when you're talking about relating things like this, having the just the straight up power spectrum, this is the amplitude, the magnitude of the sine wave and the period of the sine wave. It does not, in this case, show anything about the phase shift in the data signal. Okay.
Perfect. And when we start taking kind of Brett's comment that, well, if you got one or two loops, interaction analysis, that's not as important as when you may have 100 loops or 1,000 loops, and now you're starting to try to, go through all your trends. And the comment on the poll earlier was, oh yeah, we just use data analysis and trending, and so your oscillation detection is visual, right? It's visual in nature. You're going to pull up a trend, and then you're going to start stacking those trends on top of them and start to stare at them until you start to see those patterns and oscillations. And then you try to visually line up the periods or try to determine, well, is that a 50-minute oscillation or a 40-minute or a 20-minute oscillation? When you take power spectrum and you kind of break it into the raw data that we saw in the last trend, you can kind of transform it and look at it in a different way. And so, Brett, can you kind of walk us through the idea of analyzing multiple loops together for identifying that shared period and kind of explain the trend and the analysis method here?
Sure. So here you can see kind of a lot of information, right? So the rows in the bottom half of that plot are they are the spectral kind of density of all of the loops, right? So you can see that each row is a loop, and as you move across, you can see that you have varying intensities of a blue color. I will add that you can change the color from blue. We probably should have, but basically what you can see here is that uh, as you move through the different kind of periods of oscillation, sometimes there's no energy, sometimes you can see a lot of energy. And so then up above, we have, I think I'm seeing 4 check marks there. So we have 4 kind of loops selected with all of their, instead of showing it as an intensity of blue, up above we showed it as a plot of similar to what we shown on the previous slide. And so you can see here that the higher the peak, it corresponds with the intensity of the color down below. And what's interesting here, right, is that all of these loops, even a few there that aren't selected, have this strong peak at a period of approximately 19 minutes. I'd say that it's a little bit there. So generally you'll come into this because you have a loop that's oscillating and you put it in manual and it's still oscillating. Probably isn't because of this loop. So you can identify that loop, and then you can come over here and you can sort by all loops that happen to share that same frequency, right? So here we have a variety of loops that are, in order, and we can say, oh, okay, yeah, oh yeah, so the loop we care about is FIC 404. Oh, look, 402 is just upstream of us. Oh, wait, but actually no, 413 is actually upstream of him. Oh, cool, it's probably that loop, right? These are kind of things that you can do to help find relationships in oscillation and identify root cause more quickly.
Yeah, and as Brett had mentioned, it's kind of related to that. It's the fingerprint, right? This is the frequencies that make up that signal, and if they've got shared frequencies, that's a good way of doing determining what frequencies are within the data and which ones are shared between your different loops. So if you're trying to do root cause analysis or frequency detection, these are the set of tools that you would use. Power spectrum Fourier transforms are the heart of it. So now that we have this kind of knowledge of oscillating processes, right, we need to be able to take these loops and apply tuning to them to sometimes correct them. Now, as we mentioned earlier, tuning is not going to fix a sticky valve or a broken valve or something like that, but we do need to be able to go and approach controllers that do have diction present. And so if we're dealing with non-steady state or oscillatory and moving data, you need to make sure that your software is equipped to be able to handle those types of systems, right? If all your processes were, very, very simple flow loops that never move, they stay at set point, and you can make set point changes and things were nice and smooth and they look like they come out of a textbook, right? That's pretty simple. Unfortunately, the real world's never that straightforward, right? We're dealing with processes that are oscillating, that are swinging, that have difficulty dealing with that. So being able to deal with non-steady state data or oscillatory data is a real benefit when you're talking about doing PID tuning analysis and so forth. And so we're going to spend just a couple of slides, talking about how PID controllers can impact the oscillatory nature of a loop by adjusting the tuning parameters. We've only got a couple of minutes here, and this is normally about 6 hours of material. So again, we're gonna move pretty quick, right? But you can take within our tool set, analyze oscillatory and data to be able to generate tunings. Well, what impact does tuning have on performance? So one of the tuning parameters that is probably most influential in that is that integral term. And Brett, can you talk a little bit about how that integral action increases oscillatory nature and what they would need to do to perhaps mitigate oscillations with integral action?
Okay, so yeah, like you said, it's like a 6-hour thing, but ultimately the I term, the integral term, is going to be adjusting your baseline underneath the controller output of the process. So it's searching for the right value of the output that will get you to whatever new set point you have. Because of its kind of summing nature, it isn't making really sharp changes. It's making more rolling kind of summing changes. And so that's fine if you have a situation like maybe the bottom middle, right? That's working pretty well. But then what winds up happening is that as you start hunting too far quickly or start pushing too hard on this oscillation, this summing, it takes the previous sum that it has too seriously and overshoots, and then it has to come back around and has to keep working. So the integral term is invaluable and completely necessary in 99% of industrial processes, but taken to extremes, just because of its underlying kind of summing, rolling nature, it can lead to intense oscillations. And so, yeah, to mitigate it, you have really two possibilities. You can use less, or you can apply a little bit of derivative. So I think that's the next slide, right? So
Yeah.
look at that. It's almost as though we planned it. So basically what happens so on the left, you'll see a PI controller. And if we wanted to push that any harder, the oscillations would be unacceptable. So if we push the P and the I terms harder, we'd get a nice faster startup at the beginning, but then the resulting oscillations would make it not worth it. What derivative does, and we definitely won't get into how, but derivative dampens oscillations. So what derivative lets you do is it lets you push harder with the P and the I while also dampening the oscillations that might come from that. And so what you can see on this is that, you still get some overshoot, but you can see it's significantly less oscillatory. And as a result, what winds up happening here is that we get to set point, I'd say maybe 20% quicker on average. And so that's a benefit if that 20% is important, right? If this is a flow loop and you just went from 5 seconds to 4 seconds, probably not worth it. But if it's an oven and you just went from 5 hours to 4 hours, definitely worth it. For the flow loop, I would just recommend the other solution, using less integral. Also, yes, as Bob is indicating with his mouse there, noise is a large problem with derivative because it's generating a slope from point to point. When it's calculating its derivative, a chattery, a noisy signal will lead to increased chatter in the output. As a result, you tend to only use derivative on smooth loops like temperature, things like that.
Mm-hmm. Yeah, and the way I like to think about derivative is it tends to kind of fight that kind of inertia of temperature loops. The temperature wants to keep going, derivative pulls back before you get to set point, and it helps. But again, any of this noise that you have in the process variable gets amplified and reflected, and this is generally where derivative gets its bad name of danger, destruction, do not use, is because any noise in that process variable gets amplified and reflected in the output. And even if you have a clean signal, just throwing more and more and more derivative at it isn't the solution, right? It's not just like, oh, I got an oscillation, I'm just going to keep throwing derivative at it till it goes away. Too much derivative will really start to inhibit the ability for the controller to respond well to the process, and you end up stretching the oscillation out, not getting rid of it. And so derivative is one of those things. It has a limited application, probably 5 to 10% of loops. Slow loops, temperature controllers tend to be the most common application. Clean signals, and generally you just need a little bit. You don't need a lot of derivative to get the benefit that you need. Any more actually ends up causing more and more problems associated with it. So just to kind of wrap up a little bit on the topics, I know we've blown through a lot of material in a short period of time. We can kind of talk through just a quick case study. This was just a gas preheater on a particular system that had a lot of oscillation. It had a lot of variability, and being unable to kind of maintain this process in a constant target actually caused variability in the moisture content of some downstream units and different processes, and it just caused issues with the system, right? So we were able to take the data from this particular application, generate models, generate tunings to be able to get to the point where we could take the variability of the loop and decrease it dramatically. Decreasing variability, as we learned, allows us to do that optimization, be able to move set points a little bit up and down. And again, if you were to just take this process and move its target up or down based off of the variability improvements that you've had, you'll probably gain just 1 or 2% movement, less valve position or more valve position, depending on which way you're moving, be able to maybe use a little less utilities in the system in the long run, right? So tuning, identifying the oscillations, identifying the types of valves, identifying the source of the nonlinearities, fixing valves when necessary, tuning when required, helps you get to that variability improvement that you can see.
All right, gentlemen, thank you. Thank you both. Okay, people, you have experts here, experts. Go to your toolbar, click on Undock Pane on the questions bar, and please type in your questions for Bob and Brett. All right. With that, can you go to the next slide, please, as they type in their questions? Okay, I'm going to do one final poll. You should see it in a minute. Again, please select all that apply. Take your mouse. Have someone from Control Station provide more information about software to accurately model and tune, plant performance monitoring software. We also have excellent PID tuning workshops available to you, or a turnkey service solution to optimize your plant. All right, first question. Would you use the D term for pressure control loops?
Ooh, that is a good trick question. And so the answer is maybe. And it depends on the nature of the pressure loop. If there is a lot of noise and movement in that pressure, derivative is going to chase all of that noise, and it's not going to really give you the benefit that you're after. But if you've got an application that's like a flare or something like that, where there's safety systems and pressure, derivative can give you a little bit of a faster response than just proportional and integral attached to it. Brett, I think you probably have a comment on this as well.
Yeah, so the other thing I will mention, just so we're clear, is that you only ever need to use derivative if you're trying to push things to the max, right? If you only want a smooth, moderate response, you can get that by backing off the P term and the I term. It's only when you want to push your loop as fast as it can go and those resulting oscillations become a problem that you need derivative. So for these slow moving pressures that you're talking about, it's unlikely that you're going to want to take a huge pressure vessel to the max, right? It's very unlikely that you're going to be pushing that super hard. It's the pressure loops that you will be moving quickly are probably going to be small and noisy and quick, and so at that point the noise might be an issue. So it's a razor's edge that you're balancing on there, with pressure.
And again, it's one of those things you got to think that derivative is all about looking at that rate of change. And so if you have a relatively smooth pressure, and you're doing a constant set point and your pressure starts to spike and you want your controller to be as ridiculously fast as possible to that spike, derivative will help you. But if those spikes are noise, it's going to make things worse, right? So it depends on the objective and the nature of the pressure loop that you're trying to control. And as Brett mentioned, are you trying to get this thing to be as ridiculously fast as possible? And it all depends on the objective of the loop. I have used derivative on flare pressure once or twice with great success. I've probably removed it out of more pressure loops than I've added it, though.
Okay, thank you for that great explanation. Can you go to the next slide, please? Excuse me. Next slide, please.
Yeah, it's stuck.
Oh, it's stuck. Okay.
There we go.
There we go. All right. Thanks. Thanks, Rob. All right. We're live people. Sometimes it just happens that way. Grab your handy dandy phones, snap a picture of the QR code, and you can access more case studies, white papers done by Bob, Brett, all right conveniently on your phone. All right. We do have another question, gentlemen. In the mining industry, it is not very common to have actions towards optimizing control loops. Is it possible to share experiences in mining solutions? Bob?
Oh, Bob, you're all over this one.
Bob, you're all over this.
Yeah, mining is one of those difficult environments, right? Where it's just running is all you care about. Optimization tends to be historically has been kind of in the back seat. We do a lot of work in mining, so we've deployed monitoring and tuning technologies across many different mining sites, and the objectives are different, right? We've done a lot of work on like smelter optimization for like lance control, temperature, depth, pressure in sulfur systems, trying to get stability within the system to get just a little bit more production out of it. And that's really where optimization comes into play in mining. Is you got to go to some of the production sides of it, whether it's in the recovery systems or in utilities. Utilities is a big area where optimization efforts can see some serious dollars. On our side, smelters and some of the reclamation circuits and stuff like that, being able to stabilize the system allows you to get a little bit more production, a little bit smoother control. Even we did some projects middle of last year on a bunch of chiller systems where we were able to take oscillations down and they were able to get a little bit more efficiency out of their chillers. They weren't losing as much water, and based off the location of this site, that was a huge dollar savings because it was in the desert, right? And water is very a precious commodity there. And so if they can try to minimize how much extra water they're putting into their towers, that's a huge dollar savings. And so sometimes it's those utilities, surrounding areas, but otherwise you're going to have to kind of focus on a lot of the smelting circuit, the smelting systems, or the production systems, the circuits and stuff like that to focus in on it. And it really just kind of depends.
Okay.
But we can actually share some of the presentation. If you want to reach out, we did a presentation at Mine Exchange last year on some more specific examples.
Okay, great. Thanks, Flavio, for the question. Please feel seriously to reach out for more presentations in mining. All right, next slide, please. We're almost going to go to a wrap, but we still have time for more questions. So in North America, we have 3 individuals divided by region. We have Brian Coughlin in the Central region. Our newest member to the team, Keith Brooks, East Coast, and Alessia Testani on the West Coast. In Europe, covering Europe, we have Damian Monroe and Kathy Sweet, and they also covered the Middle East as well as Africa. So do we have any more questions for these guys? They're a great source of information. All right. Well, with that, I will wrap it up. I wish everyone a happy holiday season and look for us in mid-January for the next webinar as well as our podcast. Brett, Bob, thank you so much for doing this today.
Absolutely. Thanks.
Yep. Bye, everybody.
Have a great day.